Um, so we'd like to find characterization for global extreme points with inequality. Extreme points with for let's say for a problem like max or min. So pay attention here. We're including both subject to the constraint g of x less than g of x less than b. So we will give here a theorem that includes both the mean and the max, but for this category of inequality. Okay, so here it is. Let's introduce the Lagrangian first, or here is it. Let's write the theorem. So we need to work on an open set. Okay, so my functions g1 and 2gm are defined on open set, so open subset of Rn, taking their values in R. They are C1 functions, they are regular, so we need just this regularity. And let's consider S a convex included in omega. So S is convex. And X star, a point that is a candidate, is in the interior. Okay, the interior of the convex set. Let's introduce our Lagrangian function that will be used for both the maximization problem or minimization, so we don't have to change the function. So it depends on the purpose of the problem you are studying. Okay, g1 of x minus b1 1 minus etc minus lambda m gm x minus bm. We assume that there exists a lambda star, okay, that is a vector lambda m, okay, such that the gradient in the space of the Lagrangian at this critical point x, at the point x star, candidate point, and lambda star is 0. So it is solution of system with also lambda g star equals 0 if we have strict inequality gg of x star strictly less than bg for g from 1 to m. So we didn't add the condition positivity on lambda, so that we include both. Then we have, here are the conclusion. Then we can say that if we have lambda positive, so either they are positive or negative. Okay, so if they are globally, all the components are positive, and the Lagrangian function in space apply that at these corresponding lambda star you found, because when you solve, usually we found different points, critical points, and different points of solution of the cardinal with corresponding lambda star. Okay, so you fix this lambda and you study the convexity of the function in x. If it is concave in x belonging to S, then you have your x star is a maximum point. You are solving the problem over the set g of x, so less than b intersect S. Okay, now if your lambda star is negative and your Lagrangian is convex in x belonging to S, then you are solving a minimization problem. Your point realize the minimum of your objective function over the set, content set. Okay, so this is our theorem, and the proof is similar to the one we did when we had equality constraints. Okay, so there is no, it's just you pay attention to the small details, the positivity, the concavity, etc., etc. That's all. Okay, so let's do one example to illustrate the application of this theorem. Okay, so an example, here it is. So we are asked to solve the problem min max of the function of three variables equal, so it's the distance square to the origin. Okay, subject to g of x, y, z equal x minus 2z negative minus 5. Equality for this kind of relation, linear relation, represent the set of points of plane. So negative for less or equal, so below a certain region of this plane, okay, or above this region. So let's follow the indication. So, okay, so here it is, solution. So let's introduce our Lagrangian. Lagrangian, yes, will be function of variable space, and there is one constant, so there will be only one Lagrange multiplier. My function x2 plus y2 plus z2 minus lambda, and the constant x minus 2z plus 5. That's all. Okay. Okay, and so we solve the linear system. The system not linear, so Lx will give me 2x minus lambda equals 0. Ly is 2y, 2y only equals 0, and Lz is 2z plus 2 lambda equals 0. So and then we solve the fact, we add not positivity, lambda is 0 if we have strict inequality, x minus 2z is strictly less than minus 5. Okay, so from here we have yes, how usually we solve, we discuss. So we discuss if we are inside the inside. So if we discuss x minus 2z plus 5 strictly negative, then lambda is 0. If we substitute, then from the equations, so if you call 1, 2, and 3, so from 1 we will get then x, we deduce x equals 0. 2 gives us anyway y equals 0, and 3 will give us also z equals 0. So we have a candidate point, but let's check if it is part of the point. But here 0 minus 2 times 0 plus 5 is not satisfied. Okay, so we cannot, we don't have points in this set, so no solution. No solution when we have this condition. So the only remaining possibility is the equality when we have equality constants. So let's discuss the situation if x minus 2z plus 5 equals 0. Okay, then we from 1 will gives me lambda equal to x. 2 gives me anyway y equals 0, and the third equation gives lambda equal minus z. Okay, so let's replace, substitute in the equation. Then we will have so x is lambda over 2. Okay, so if I substitute, either we can deduce a relationship here, then yes, from here we will get then the linear relationship, we keep it, and we have 2x and 2x equal minus z, that is z equal minus 2x. So we will substituting then, so z equal minus 2x, and you will have here x plus 4x plus 5 equals 0, which gives me x equal minus 1. Okay, minus 1, and z then is equal 2. Okay, so the candidate x star, y star, z star is the point minus 1, minus 1, 0, and 2 is a candidate. Okay, so is a candidate. Okay, for a maximum. Since lambda, what about lambda? With lambda star is 2x, so 2x is minus 2, so it's negative, so it's a candidate for maximality. So we should check if whether L, the Lagrangian, is concave. So what about Lagrangian now? Concavity of L in space with minus 2. So the Hessian of the Lagrangian will be the derivative Lxx is 2, 0, 0, 0, 2, 0, z0, 0, 2. Yes, it is strictly convex. This is strictly convex. You have d1 xy z equal to positive, d2 will be 4 positive, and d3 is 8 positive. So L, yes, L is strictly convex. L minus 2 is strictly convex. But then the point is a minimization problem. Is it, but my lambda, what is lambda? Is 2 times x. What is lambda? 2 times x. And x, we found it is minus 1. So is there something wrong here? I think there is something wrong. Ah, yes, lambda negative. Then we check for convexity. Okay, not concavity. We need more convexity. Convexity. Okay, is strictly convex, and our lambda is negative. So yes, so the point minus 1, 0, 2 is a global mean. Okay, and it's not evident to see that yes, it is like that. Okay, so you see how to apply the method. So yes, as a remark also, we didn't need here the regularity of points. Okay, just to put it as a side here, remark. Regularity didn't involve, okay? Regularity of x star is not necessary here. Okay?